Our next speaker is Paolo Longo, uh, and he will tell us about the advances of how we can optimize uh, ThermoFisher microscopes. Please, Paolo.
Uh, Thanks a lot, Gerd, and hello to everyone. So I hope the workshop the school actually is going well. You're learning a lot, and I want to thank the organizers for the opportunity of giving this presentation and tell you a little bit more about automation in ThermoFisher microscope. So basically, in this presentation, we're going to talk about scripting, automation, and essentially how we could get some machine learning and AI for advanced TM application. I'm sure you're going to have a lot of hands-on, a lot of practice. So this is going to be a little bit the foundations. So just to give you a little bit of an idea, like when we talk about atomic resolution TM characterization, I just want to go back a couple of decades. So the first aberration corrected microscope were introduced between the year 2000 and 2010. So around this decade, we had the introduction of atomic resolution imaging. And back then, there was a very limited hardware and software integration. It was very tiny. And the detectors back then were very low sensitive. And, there was a small data output. Things got better, the other decade, the following decade. So where we had higher resolution, higher stability, detectors got faster and more sensitive, and also the software and hardware integration improved. Then we got into this decade where we're starting to see more and more automation and AI emerging. We also see more and more multimodal data acquisition. So in our microscope now, we're trying to combine more and more techniques. And a lot of times we want to run these techniques simultaneously so that you can get better information from your sample. So what we expect, moving forward is essentially for the remaining 5 years of this decade, actually the remaining 4 years of this decade is that we're going to see more and more automated analysis. We're going to have this data-driven multimodal insights. We're going to improve the stability of our microscope. We're going to have even more and more integration. So just to give an idea, so what is the challenge right now? So the challenge are actually it's the materials are evolving faster than our tools. So as I mentioned in my previous slides, we've seen over the last 2 decades massive improvements in the hardware technology and also the integration between the hardware and software hardware integration. But the way we run the experiment, for the most part, is still very old style. So you're the operator, you're sitting here, you set up the microscope, you take data. You have a lot of different techniques now, and the hardware is actually very powerful, very sensitive, very fast. So you can generate a lot of data at the same time. So you acquire data, you have to choose the right technique, you collect the data, and a lot of times you process the data, so you interpret the data and make sure that actually the data is good. Otherwise, maybe you tweak the conditions and you move to another area. This is actually very labor intensive. And actually all this process limits the speed and the efficiency. So you can see the operator is sitting here and it's kind of like the core of the whole experiment. But I think something useful like in the future is that we start to separate a little bit the operator from that core position, and now we have actually AI play as an adaptive feedback. Essentially, you only have to tell what kind of information you want to get out of your the specific specimen. The techniques, so the right technique that will be chosen. The experiment will start. Data will be generated, but at the same you have this feedback loop that will basically automatically tell if the data is good. If the data is not good, you will move on to a different area, so we'll change the condition. So the benefit of this is that you have automation and reproducibility, you have real-time data-driven decision-making, multimodal data integration, and faster discovery. Again, as I mentioned before, we have a lot of techniques available, and we want to make sure to have them nicely integrated. At the same time, we want to make sure that we pick the right technique. So this is very important, and we're spending actually a lot of effort in the development for multimodal data integration. So a lot of now, now that we are in AI automation training school, but sometimes we say, is AI and machine learning, the ultimate solution? Do we need to improve the hardware? So, and at the same time, AI is only powerful as the data it learns from. So always data starts with the hardware. The better the data is, the better the automation is, okay? So hardware defines the data quality, and AI will define the data value. So, and then the true progress always comes from the synergy between advanced instrumentation and intelligent algorithms. So obviously, why we need to improve the hardware? Because we want a higher stability, higher sensibility, higher speed, and that would actually improve our AI models. So if we have improved detectors and integration, we can enable more accurate automation. So, and also these accurate and database are important for AI learning and validation. And it's very important, as I mentioned, to have a robust and reproducible hardware. This is, again, vital to train and validate a reliable AI solution. And also, like the materials are getting more and more complex at the same time. This requires both smarter tools and stronger systems. Okay, so if we look at the recent, actually, let me play the whole thing. Okay, so if you look at the research trends in script-based microscopy, so basically with automation and with scripting in particular, we're able to increase the throughput dramatically. We also are able to increase the reproducibility. Scripting offers a path forward toward highly repeatable acquisition with little variation. This is a very important option for creating training database for AI and machine learning. So we can, as I mentioned before, we can increase the potential for throughput, to increase the throughput. This would be great for identifying areas of interest and processing data. But at the same time, we could get much better access to new insight through massive sites of data. So again, as mentioned before, detectors are getting faster and faster. You're generating more and more data. So you want to be able to actually get a faster insight into this data. So now, what actually changes when we move from manual microscopy to scripted microscopy? The biggest difference is not that the microscope becomes faster, it's that the experiment becomes controlled. First of all, all the hidden decisions that an experienced operator makes become now explicit instructions in the script, instead of rely on memory or personal habits. The second, because every action is now specified, the exact same experiment can be repeated tomorrow by another user or another instrument that give us a true reproducibility. Third, the microscope can now start reacting to the data is collected instead of waiting for the operator. And now we have, finally, we have here the metadata. So we can do quality checks. We can implement quality checks, stopping rules. So now every acquisition is fully documented, and the experiment stops because predefined scientific criteria have been met. Ultimately, scripting is about improving scientific rigor. We're not just automating clicks, we're encoding the experimental method itself. So this is a very nice slide that actually illustrates what the situation is it's kind of like an analogy when you try to go for the treasure hunt, or in this specific case, to try to find a mushroom in the woods. So many microscopy sessions, unfortunately, become what we call like a treasure hunt. So we sit down with an interesting sample, spend hours searching something exciting, and eventually come away with one beautiful image, but often without a repeatable workflow or statistically meaningful results. Scripted experiment changes the mindset completely. Before the acquisition even starts, we define the inclusion criteria, what makes a region worth measuring. Also, we define the acquisition order, the allowable, so that the electron dose that we want to use, and the conditions that determine whether the experiment should continue or stop. The script then executes that experimental plan consistently every time. So every image is now acquired under a known condition, every parameter is recorded automatically, and every decision follows a predefined logic. The result is an experiment that is repeatable, traceable, and easier to reproduce across different operators. So basically, scripting is now transforming a microscopy session from an exploratory search into a well-controlled scientific experiment. Now, our scripting interface that I'm sure you guys are now practicing with is called AutoScript TM. This is what we have in ThermoFisher. So basically, what is AutoScript? AutoScript is just essentially it's providing like an API, and that gives you access to every microscope state, and they can give you access to the detector control and pretty much everything else. So this is actually very important because that, as I said, will give you access to the microscope, and you can basically script and control every possible piece of hardware inside the microscope. But this is actually very important for automation. So a quick example that I want to show you, this is something that we actually created for marketing purposes some time ago when we started promoting AutoScript. And it was basically like a drift correction. And, normally drift is something reproducible, something that you can actually track in real time, and you can correct in real time. This is something that was done with AutoScript in a matter of 3 hours. Now, you see a massive drift. Obviously, our microscope don't drift as much. We induced a pretty massive drift to, prove that the script works really well. So this is actually, again, an example of AutoScript with, one of the most difficult problems that every microscopy tried to solve, which is the drift. Another example of AutoScript script is essentially try to do something that is not available in the microscope. In this case, so this example is actually applied to some battery material. So here we wanted to look at traces down to the atomic level in a beam-sensitive material, very complicated. So normally, when you scan the beam, you always go from left to right, and you create an image. But if you want to do different type of experiments, you want to rock the beam, that functionality is not present in the software. At the same time, you want to do EDS, that functionality is not present in the software. And that would allow you to create an electron channeling pattern, which is very important to actually identify the position of atomic species. So this example was applied by the combination of Velox and AutoScript, and we created something called Alchemy, which stands for atom location by channeling enhanced microanalysis. So this is actually very important because we wanted to map fluorine dopants in the lithium battery cathode materials. And we tried EDS, we tried EOS. Obviously, EDS is impossible, the TM, to see the lithium. We could see lithium in EOS, but we couldn't map it down to the atomic level. So we were not able to solve, to answer the most important question, which was where the lithium is located. So we use this approach where you basically spread the beam over a very large area, and you rock the beam. And for every tilt, you collect an EDS spectrum. And then automatically you build all these tilts in an electron channeling pattern. So you can tilt the sample into different direction and repeat the experiment. And that is fully automated. So actually this script is already available for those of you who want to try. And long story short, you basically check the channeling pattern of different atomic species. In this case, fluorine, oxygen, manganese, and titanium. And you can see that when you tilt to the 1,1 zone, you can see that the pattern of fluorine corresponds to the pattern of oxygen. You see the other two are different. These also correspond to the what we have in what we can do through simulations. So that tells you that the fluorine is at the same atomic column as the oxygen. And that actually answered the important question that it was impossible to answer with other techniques. And it also was done on a different specimen here, looking at traces of lanthanum in strontium titanate. Depending on the performance of your EDS detector, you can speed up this acquisition. On the Super X, this acquisition took 24 minutes. If you had an Ultra X, which is 6 times more sensitive, it would have taken only 4 minutes. So this is actually relatively fast. Another important practical example of how scripting can improve interpretation of microscopy data is basically on DPC. So this is a very nice example, and actually I want to acknowledge my colleague Austin Wade, who ran the experiment, created the script, ran the script, and this is something extremely useful. So what the next few slides that I'm going to show you are actually quite impressive. So there should be a video. Yes. So here we're playing like a video. So of this video shows differential phase contrast or DPC, imaging magnetic domains. So here what we're doing, we're tilting the sample. As we tilt the sample, we can observe static magnetic. So we can follow about these domains respond dynamically to changes in the orientation. So let me play the video again. Okay. So you can see that in the video. This is actually an excellent example where automation and scripting allow us to acquire a reproducible data set that would otherwise be tedious to collect manually. But what is but before we interpret the images, I think we need to understand a little bit better where the DPC signal comes from. So this is the setup of our Panther stem detector. We have 2 different sets of detector here. So we have the bright field, which is divided in 8 segments, and we have a dark field detector that is divided in again in 8 segments. So the segmented stem detector measured the displacement of this segmented detector, measure the displacement of the electron beam. This is actually caused by local electromagnetic fields inside the specimen. The individual electron detector segments are combined to produce this DPC map. So you can see here. So you create like a DPC map, where color represents the direction of beam deflection. Although this visualization is very informative, it still requires the user to mentally translate the beam displacement into magnetic field. Okay, so this is so here we try to reach an important challenge. The DPC image tell us the direction of the beam displacement, but we want to know the direction of this magnetic field. This is not something that something that is embedded here in this image, but it's not evident. So we need to try to extract that information. Okay. So for example, if we have this domain A, if we want to know the magnetic field, the answer again is not immediately obvious. So this is actually where scripting becomes very important. So you can see the example there. And this is something that we can use to automate the whole process. Just to give a little bit of, this is just a core of, the script that I'm going to talk about. So this slide actually summarizes the underlying physics. So the electron beam is deflected by both electric and magnetic field. So, but what we measure with a DPC signal is just the beam displacement. So what we're doing here, we're using the known mathematical relationship, and if we know that, we can automatically transform the DPC vectors into magnetic field vector and electric field vector. And this is something that can be done via scripting. Actually, when we do that via scripting, that can be automated. It can be the information available to the user. And we applied the script. And now you can see on the left, this is a standard DPC visualization. In the center, essentially, is this converted to magnetic field direction, and the other one on the right is the electric field direction. So now we have all these three different color maps. Obviously, we want to try to combine everything together. In this specific case, we're interested in magnetic field. So basically now, rather than relying on colors, AutoScript overlays the magnetic field vector directly onto on top of the image. Now, every domain has an explicit magnetic field direction. This is actually dramatically reduce interpretation time and makes the communication of the results much easier. And this is very important, especially for a less experienced user. And this is one of those experiments that are considered, relatively difficult, at least for the type of information that we want to obtain. So you can see the arrows here. So this is actually where scripting becomes important especially in the case of decision making. So instead of going around and collecting high quality data set, we can actually script the whole process. So you can the script actually in this case would evaluate simple metrics. So it would evaluate the magnetic field orientation, for example. This is the important information that we want to extract in the specific case. And if the microscopy is, if all these criteria are met, the microscopy automatically will launch the higher value acquisition. So, and this is an example that you can see here. So you can see your you can see all your magnetic field vectors here. So this is a very nice example of something that you can obtain through AutoScript with scripting. Another example that I want to show you is essentially frame-based precision that you can trigger by AutoScript. And just a couple of examples that I'm going to show you. One is on strain analysis, and the other one is basically try to break channeling conditions and improve quantification down to the atomic level. Okay, so I guess for those of you who don't know what precision is, essentially we are rocking the beam and tilt by tilt you collect an image. Okay, this is actually very important for crystallography. So you can dramatically improve quantitatively. You can improve your strain orientation mapping. You can improve spectroscopy because you are down to in the case of the case of crystals. Okay, so let me show you these two examples here. So normally we have a conventional precession where you process the beam at each pixel, you move on to the other pixel, okay? And then you have a frame-based precession where basically you do like a tilt and then you collect the 4D stem data set. Then you do another tilt and you collect the other one, okay? So this is the two different approaches that we have. So what we're trying to do, we're trying to script, the frame-based procession. So these are the three different examples here. So here you have an example when you tilt the beam only 16 times. And so you can see an improvement already in the information. If you do 32 steps, you get even a further improvement. So you can decide how many steps you want to do the tilt. And this is an example of strain profile using precession. No precession and with precession using this frame-based precession. You can see the improvement in the strain profile when you apply precession. And that was done by scripting using a frame-based approach. Okay, so the script allows you to have everything nicely tied together. Okay, so another example that I want to show you for scripting, this is more relative to the Iliad. For those who are not familiar with the Iliad, this is our latest, our flagship microscope that we launched, we introduced in the market 2 years ago, a little less than 2 years ago. And it comes with an electrostatic beam blanket and a ThermoFisher energy filter, all hardware and software integrated. But obviously there's quite a lot of experiments that you can run, with a blanket. And essentially you can go for, this is an example, this is a presentation that I gave last year. But you can have situations where you want to try to use the blanket and essentially scan the beam in a random way, okay? And actually try to reduce the number of points that you touch, and then you reconstruct the image. In the specific case, we only probe 50% of the pixel in this case. And you could use a different type of scanning patterns here. And that would actually give you different results. Actually, in this specific case, we're getting a better contrast in the maps. And you can also decide to script in a way that you can probe 25% or even less. So you can also create your mask and decide that you want to scan the beam. And every time you hop from 1 point, 1 pixel to the other one in the image, you're activating the blanket. So this way, you can actually reduce the dose that you are dumping on the specimen. This is very important, especially for beam-sensitive material. We found the blanket extremely important when you deal with beam-sensitive material. Another example is electrode dose painting. You see here the Gioconda, and you can see, I believe, a strontium titanate image on top. So here, the strontium titanate image was used using the intensity level, normalized to the intensity level of the original Gioconda. So you can see here on the forehead that there is brighter, here on the chest there is brighter, you have more intensity. On the hair, that you have less intensity, you have less intensity in the image. So this is also a script that is available for those of you who work with the blanket and have access to the Iliad. So we believe, the blanket is actually, and the combination of scripting is going to enable a lot of different modalities, which are very important for beam-sensitive material. So basically, scripting is actually very important, and AutoScript TM is supported on all ThermoFisher STEM platforms. So we have the Iliad, TIMI Spectrum, and the Talos. And a lot of times you can actually take a script from one instrument and use on a different instruments, depending also on the information that you want to achieve. Okay, so this is just to give you a little bit of an introduction on AutoScript, show you some example, the power of AutoScript. But as I mentioned at the very start, AutoScript also provides an AI. It provides an API. And normally, like we see AutoScript as the AI enabler, and I'm going to show you some examples here. So AutoScript provides the API to connect the AI service. Normally, the typical workflow is you have to import the segmentation model to be used for a specific task. The data is collected in AutoScript environment. The AI server grabs the data from AutoScript. The analysis is carried out by the AI server, and the results of the analysis display in the AI server. So you can see here a little bit the representation of what it is. There's also like the software here that shows you some that you can access to download some example of scripts. I want to show you a couple of examples here where this becomes important, specifically in the case of adaptive scanning, which is actually very important, especially when you look at nanoparticles, or you want to look at specific regions in the specimen with more dose, higher dose, and other regions with lower dose. So we believe adaptive scanning is extremely important. And I'm going to show you two examples here. So the first example is analyzing nanoparticles on the substrate, and the second sample is to do to basically get high quality atomic images with the least amount of dose. So essentially get the best quality atomic analysis, and the case that I'm going to show you with EDS, with the least amount of dose. Okay, so the first example is, well, first of all, let's try to understand what adaptive scanning is. And this is actually the result of a collaboration with BSF. This example is a little old already, but normally you collect the stem image. And again, just to give a little bit of context, BSF is one of the largest chemical companies also working on catalyst. So normally TM is very important to them. They want to know the composition of these particles. They also want to know every type of information. But normally, like in old-fashioned way, where the operator has to take all these images, you basically, you're forced to only probe a few nanoparticles. But in reality, you want to get as much statistics as possible. So this is where automation becomes important. So here we have, you take a fast overview of the image. You can barely see these nanoparticles here, but this is actually easy because you can use a neural network to identify this particle, essentially to segment this particle here. So you see all these particles here in the image, nicely segmented. At that point, you want to scan this region. First of all, you want to know every type of information out of these nanoparticles, but at the same time, you want to scan only these particles here. And if you think about these particles, cover a very small area of the specimen with respect to the matrix. So most of the image, majority of the area of this image is actually matrix, but you're only interested in these nanoparticles. So you can decide you can tell, you can do the experiment in a way that the beam is only spending most of its time in this particle as opposed to the matrix. And then you acquire EDS. Okay, so you start from the image, use neural network, you segment the image, so you find all these nanoparticles in the image. At the same time, you could do all possible kinds of analysis, like shape interpolation, statistic, number of particles, etc. Then you can apply a mask and do EDS. Okay, you only do EDS across these particles here. And then you give information on the composition, and then you tie this, you take this compositional information and all this shape information on a report. And this is something that is available. So this is something that you can reproduce over multiple areas in the specimen. And you can also stitch all these tiles together. So here, essentially, they were able, using this approach, to map almost 5,000 particles and get every kind of information out of these particles, from statistical information, sites information, to like compositional information. And the entire acquisition took only 23 minutes. So it's actually quite incredible. With only 23 minutes, you're able to probe 5,000 particles over a very large area and across the specimen. If you wanted to do this manually, it would have taken an acquisition time of over 25 hours. So you're seeing already the improvement of by using this adaptive scanning. So you're getting the best quality data in a fraction of the time. So imagine all the dose that you're saving. So the data is actually more reliable and more accurate when you're depositing a lower amount of dose. I want to show you now another example along the same lines. So this is actually doing high resolution STEM imaging. So this doesn't look a great image, but again, that was the purpose. So you could barely see, the atomic column. The specific case is strontium titanate. So you see the strontium atomic columns here. But no, you have the contrast is good enough that you can actually identify both the columns of strontium and the columns of titanium. Okay, so you can identify them. And at this point, you can set up the experiment to have a dual speed pattern, meaning that you can apply different speed. So you can have, in this case, you can spend 3 milliseconds on top of these peaks here, these atomic columns, and 3 microseconds when you go from one column to the other one. Okay, so this is very important because again, like in the previous case, we spend most of our time probing the metrics. Okay. At the same time, you can also apply drift correction. So this is very important because in order to improve the statistics, you want to probe the same area multiple times. But as you go with time, obviously, you have drift. So you want to be able to correct the drift. This is something that you can set up also as a part of the process here. Okay, and then you do an atom identification, so you can identify your atomic columns, and you can also put some metrics so you can tell when you want to stop, because this is going to be a loop. You take you map an area, you do your EDS, but at the same time you might need more statistics, so you have to go back to the same area and acquire another and run another analysis and doing drift correction. You don't want to do this indefinitely. You want to stop at a certain point. So you can actually set up that. The way it was done in the specific case, again, we see here. So first of all, you have to create an atom probability prediction map. So you can see that the contrast follows the original image. Then you put a binary mask here so you can identify the columns. And at this point, so you know exactly which columns are strontium, which columns are titanium. And at this point, you can do one acquisition with a dual speed. And so each acquisition takes about 1.36 seconds and 1.8 seconds for processing. And you can go back over and over the same area until you build some statistics. So there's also a drift that can be corrected. Now, how this works. So this was done again on a Talos, which is non-aberration corrected microscope. So normally you do, this is actually this is the very first frame. The very first frame, you identify all this column, you do the EDS at different column, and then you could do titanium strontium peak ratio. And based on that, you can define the statistic needed, whether the statistics is good or bad. Okay. And you could go over and over until you can, the error actually goes to 0 in this specific case. So that tells you that you reach already the best possible statistics. So basically you stop acquisition after at the 20-second frame. Each frame took about 1.3 seconds. So basically you have a total of 30 seconds of beam time onto the specimen. And you're getting a very, very high quality atomic EDS map. To get the same quality with the same dose, you would have per atomic column, it would have taken 394 minutes. So you're doing the same with in 43 seconds. Essentially, you are depositing onto the specimen 550 times less dose. This is a very important achievement. So I just want to show you some example AutoScript can enable AI analysis. In the specific case, this is kind of like denoising or probability map. So the image on the left was acquired with 800 electrons per angstrom square. And the second one is basically the AI-enhanced visualization. Is a probability map. So you can see a very nice example here. You can clean up your image. And I'm going to show you like a video here where this is a similar example to what I discussed before in the case of BSF, basically finding particles and try to get every possible type of information out of these particles here. So here we're launching the application here. So you see that basically you asked AutoScript to collect an image, then you're using your pre-trained neural network here, and then you could get your results here very fast. So this video is actually the speed is increased, but like overall, it didn't take very long. It was just a matter of probably like 2 or 3 minutes, so very fast. Now, in summary, hope I've been able to show you that automation improves reproducibility and throughput. Scripted workflows transform manual procedure into repeatable experiment. AutoScript also provides a complete microscope programmability. This is very important because you can enable custom acquisition, hardware control, real-time processing, and also create these advanced experimental workflows. At the same time, scripting unlocks new microscope modalities. So I showed you the example of drift correction, rocking beam and stem, DPC visualization. This is a beautiful example where you can actually separate the contribution of magnetic field or electric field in DPC images. And also I showed an example of frame-based precision. And we also show you the adaptive scanning. The AI will enhance, but not replace the microscopies. So this is going to be very important for intelligent feature detection, automated decision support, rapid quantitative analysis. And again, in my opinion, materials are becoming more and more complex, and some of these technologically important materials are extremely beam sensitive. So you need to be able to create the best possible strategies to optimize the dose. And scripting is very important. I'll show you one example with in the Iliad with a beam blanket. There's a lot of automation that you can create there, essentially tailored around experiments. The future is obviously autonomous and adaptive microscopy, closed-loop experiments where acquisition, analysis, and decision-making become part of one intelligent workflow. And with this, I just want to thank all of you for the attention. I think I'm using less than my 1 hour time. If you have any questions, let me know. Or you can send me an email. I think my email is here.
Did you see I didn't check. Okay, let's see in the chat whether there is somebody. Okay, we have some questions in the audience.
Mm-hmm.
Okay. Okay.
So for offline testing package, like I was wondering like what kind of functionality is there?
I'll translate it for Paolo. The question was about the offline package of AutoScript and what kind of functionality it provides.
Oh, yes, I forgot. Thanks for the question. I actually forgot to mention that we have an offline package, which is actually, in my opinion, is very important because creating a script nowadays is very easy. I've seen people creating script using ChatGPT or even using Claude. But the most difficult part, also the most time-consuming part, is testing the script on the microscope. And this is also the reason why we're providing an offline version of the script. Don't recall the exact name. I think it's called, it's either offline or simulator, but that is also available.
That answers the question? Yeah, okay, I would think so. It was quite. Anybody else here in the online audience? Takes the opportunity to ask Paolo, since we have him here. It's very rare that you can get him.
But if you invite me, I'll come.
Okay, so here we have another question. Do you want to come and answer? You can directly.
Oh, I forgot to have my email
Here he
back
comes.
here.
Thanks for the introduction about the automation script. I have a question. So, is there any safety guidance to protect the device itself when we utilize AI to making the operations on the devices?
Yeah, that's a very good question, but there are because when you do when you use AI, you still need to use AutoScript to grab to basically tell the microscope to execute a job, right? So, and there are some barriers built within within AutoScript. For example, you cannot tilt the stage indefinitely. So there are some barriers there. And actually, when AutoScript started, there were more barriers that were trying to actually ease this barrier. But I want to make sure that you cannot damage the microscope as a result of scripting.
Thank you.
Okay. You also AutoScript in action here already, right? So
Yes.
we used it all the way through the first few days. So this was very nice, more in-depth summary of what AutoScript can do. We were just assuming that it does everything, okay? We weren't really going into that too much. Any other questions here? Okay. So you have a question in the chat here, Paolo. Can you see that? Okay.
Maybe, but I don't know how. So I'm not familiar with Zoom, unfortunately. So where would be the chat? I don't know if you can read, that would be faster if you read.
Okay.
Oh, the chat is here. Okay.
So is there a plan to build a bridge to Gatan and MPAD?
Oh. So okay, so MPAD is going to be AutoScript compatible. So we're going to launch MPAD G2 like in 2 months' time, IMC. In the case of Gatan, I've seen a very nice example from actually from University of Tennessee, from Gerd and Sergei's group, where they were able to actually control both the microscope and Gatan outside. Very nice example where you were actually doing I think it was, I don't know if it was diffraction and yields, but you were actually doing yields across nanoparticles, but only across the edge of these nanoparticles. So where the sample is thinner, so basically more suitable to yields. It's already possible to do that, through an external server, and that external server also control Gatan as well as ThermoFisher. And I mean, Gert, Sergey, you guys know this example way better than I do. I don't know if there's more to comment on that.